I'm very sad. I'm having technology issues. I did this on my other computer and it didn't work at all. You couldn't see my beautiful face. So I have to do it all over again. So I'll try to be quicker this time. Igneous rocks. Let's talk about them. Okay. So igneous rocks are formed from a substance called either magma or lava. So you probably know this already. So basically, magma is melted rock material. So if you take rock material and melt it till it's completely liquid, all the minerals that make up that rock are completely turned into liquid state. Okay, mostly into ions. And what happens is if that liquid rock material that has like different components, different melted minerals in it, is inside the earth, we call that magma. When it's exploded out onto the surface, or at least extruded out onto the surface, we call it lava. Now, there's a reason for making a different distinction. It's not just where they are. There's something kind of important about them, and that has to do with the chemical makeup of them. So magma inside the earth and lava outside on the earth's surface. When this magma gets on the surface, the minerals that are present melted in this magma are also present melted in this lava. So chemically, from that perspective, they're the same. What's different is this: magma tends to contain quite a bit of dissolved gases, mostly water, carbon dioxide, and sulfur dioxide, and they're held under pressure by the earth. So there's these pressurized gases that are present in magma, but when it gets to the Earth's surface, it's basically uncorked and the gases come out, which is what you see up here. So the lava doesn't have those gases in them. But apart from that, it's the same minerals. Okay. I seem to be freezing up. I hope I'm not freezing up when we actually see this. I hope I get all the way through this before my whole computer doesn't freeze up. Okay. Igneous rock. So igneous comes from the word, same root word as ignite, fire. Okay. So basically, fire rocks. So igneous rocks are ones that are formed when liquid rock material cools, forming these interlocking crystals. And that makes it very durable compared to other rock types that we'll talk about. Now, igneous rocks can occur in two types. They can either be intrusive or extrusive. You know what? Let's talk about extrusive first. So I'm going to skip down here and talk about the extrusive. That means it was extruded onto the surface, okay, the exterior of the Earth. Well, guess what? It's going to cool very quickly up there. And when things cool very quickly, there isn't much time for the individual ions that make up these crystals to find each other. And so as a result of that, you end up getting very tiny crystals form. You get the same minerals forming. If you had, whatever 5 minerals you had in the magma, you're going to have in the lava, but they're going to be smaller crystals. Now, when it's intrusive, it is going to cool inside the world, and essentially the world is acting like a blanket, which is slowing down the rate at which energy exits the magma, which means instead of freezing in a matter of minutes, it might freeze over the course of thousands of years, which gives these crystals a chance to get much larger. So what happens is when you look at a rock, you'll see these interlocking, if it's igneous, you'll see these interlocking crystals, but if it's intrusive, you can see them with your unaided eye. They'll be big enough for you to see. They had time to form these larger crystals. By large, sometimes a couple centimeters. But in an extrusive one, they'll be millimeter size. So they're very difficult to see without a magnifying glass. So just here's an example. So here's granite. You can see these interlocking crystals. There's about 5 different crystal types. I could tell you what they are if you're interested, but you can see them with your unaided eye. You can see how they're interlocking. Now basalt is chemically different. It's made of a different mineral suite, if you will. But the crystals are much smaller. They're still interlocking. They're still very durable. But you can't really make out the individual crystals with the unaided eye. These are taken from the same distance away. One thing also too, a lot of times with extrusive rocks, you can see these vesicles from the outgassing event that happen. Not always, but sometimes. Now let's talk about the fun stuff, okay? Volcanic eruptions. Oh man, if I could do my life over again, I think I'd be a volcanologist. I've seen a few volcanoes in my lifetime, and I am addicted to them. I mean, seen from a close distance, they're so cool. Okay, so here's the idea. As magma pushes up on the Earth's crust, eventually the Earth's crust will fracture. And when it does, it's exactly like this. You take a bottle of soda, shake it up. It's under pressure. As soon as you crack the lid, the pressure inside drops and the gas comes out of solution and it just sprays stuff everywhere in a kind of violent fashion. That is exactly analogous to what happens with the volcano. As soon as that crack happens, the pressure in the magma drops. All that water vapor that was contained in there under pressure, all that carbon dioxide, all that sulfur dioxide suddenly comes out. And so these bubbles form, and as these bubbles rush upwards, they throw stuff up in the air. And this can be quite violent at times. So violent enough that it makes explosions that can be heard around the world. Or not, okay? But basically, that's what causes an eruptive event, is this release of pressure that happens when a crack occurs, and these gases come out of solution. Now let's talk about this stuff called silica. So silica is what quartz, the mineral quartz that you might have heard of, is made out of. It's what sand is made out of, mostly, like what's called mature sand, white sand. And it's what glass is made of. Glass, to make glass, they just get this very pure silica sand and they melt it down. Now here's why it's important, because magmas that come from the ocean crust tend to have very little of this stuff in it. But ones that are formed from continental crust tend to have a lot of it in it. Ones that are formed from subduction, it turns out that silica has a very low melting point compared to all the other minerals. So what we find is that when this rock here froze, this is a continental rock. Granted, it has a lot of silica and a lot of quartz. It's kind of like the clear stuff we see here. It's the last stuff to solidify. The other ones might have nice crystal shapes, but it'll be kind of all in there because it's the last stuff. So it's the last to freeze and the first to melt. So when subduction occurs, it's the first to melt. So we find that subduction zone magmas tend to have a lot of silica in them. All right. Well, here's the thing about low silica. Low silica leaves. I'm just going to skip forward here just a little bit. So I'm going to skip forward. I'm going to skip forward. I'm going to skip forward. Come on, let me skip forward. No, I'm trying to skip forward here. Okay. So viscosity. Viscosity refers to the ability of a liquid to flow. Okay. So basically, if you're a high viscosity liquid, you have a hard time flowing. You're like toothpaste or syrup or motor oil or high silica lavas. Okay. So it's very sticky, it's very viscous. Low viscosity fluids like water and gasoline, or low silica lavas, they flow much more easily. So they tend to be very runny. All right. With that in mind, viscosity, high viscosity means that you don't flow very well. Low viscosity means you do. Let me just try to see if I can get back here. Okay. So let's look at a low silica lava flow. It just flows like rivers, right? Let's just let it go for a couple more feet here. Let's see. So this is Hawaii, Hawaii is derived from mantle material, and mantle material doesn't have much silica in it. And so you see, it's just like, I mean, look at that. Okay, that's what low silica, low viscosity lava looks like. Now let's see if we can try to go. Let's see. Okay. Now I can't show you high silica lava because usually it just blows apart. Okay. It's very difficult to actually get up and see it. But glass is basically pure silica. So let's just take a look at this real quick. I'm going to try to mute this so I don't have to listen to these guys talking in case they say things I don't want you to hear. I mean, I'm not trying to be biased, but they don't look quite like the kind of people we want to have talking to us. Okay, so basically, here's what the guy's doing. Inside this, he has white hot melted sand, okay, silica. And you can see right there that it's so viscous that it won't even drip off that. It just gloms onto it like jelly, okay? So this is what high viscosity looks like, and this is just pure silica. So lavas that have a lot of this in them, they don't flow very easy. They tend to glom together. That's why you don't see them running down hills, okay? So let's just try going. Okay, I don't know what that's supposed to be. Okay, here we go. Okay, so different volcanoes are derived from different lava types. All right. So if we look at like Rift Valley volcanoes or hotspot volcanoes or mid-ocean ridge volcanoes, these are mostly derived from mantle material. And mantle material has very little silica in it and has very little water in it. So as a result, because they have very low silica, they tend to be very runny. So when the lava is extruded on the surface, it just flows down the side of the mountain in these rivers. And as a consequence, you get these very broad, like low steepness volcanoes called shield volcanoes. You know, one example of one, Jeju Island. Jeju Island is just one large shield volcano. And in fact, it's a UNESCO World Heritage Site because it has these world's longest lava tubes. Those lava tubes are basically lava rivers that froze on the top but didn't flow underneath, freeze underneath, and they did the lava just kept flowing because it had such low viscosity. Kilimanjaro is another example. Hawaii is another example. Now, subduction zone volcanoes tend to be considerably different. They tend to, as I said, because the silica melts first, they tend to have a lot of silica in them, and that means they tend to form much steeper side volcanoes. So a lot of the really iconic ones like Fuji, Mount Rainier, Mount Etna, Mount Vesuvius. So these ones, Krakatoa, they have very steep sides to them because the lava doesn't flow down its sides. It often comes out in just chunks that just kind of land on the hillside as boulders, really. And it's worth noting that a lot of times there's multiple different magmas characteristics. Like sometimes the higher viscosity stuff comes out first, and then later on in an eruptive event, the lower viscosity stuff will come out over it. I don't want to mislead you. That's why we sometimes get these things called composite cones. All right, this is my artwork. I'm not proud of it, but I tried. You got to give me that. Okay, so here's what I'm trying to show. If I have low silica, low water content lava, what would I expect to happen in my eruption? Well, what would happen is because there's low silica, it flows very easily. And because there's low water, it's not going to be blown up into the air. So it's just going to kind of ooze out like we saw in that first video. And it's just going to flow down the side in rivers, forming a shield volcano. Okay? These are things you can walk right up to and look at. like in Hawaii. Now, keep a low silica content, but now add some water to it. Well, what you're going to find is it can flow very easily, but now it's being pushed. It's got this explosive character. So now it's almost like a fountain you would see like at a park or something like that. So, but it's a red hot fountain. Okay, so the lava is flying up in the air, but it's not exploding because the lava is kind of moving out of the way of the pressure, is letting the pressure out before it builds up to any kind of explosive way. Now, I mean, maybe you know that about bombs. To have a bomb, you need to have gas pressure and you need to have confinement. Well, there's no confinement when you have low silica, but when you have high silica, it's different. Now, I have high silica, so it's very viscous, can't flow very well, but I don't have much water. So what happens then is I just get this kind of glommy form. On Jeju, there was like a late stage activity that happens on this, near Sagwapo, this famous Buddhist temple that I was just at. It was formed this way. So it's just like toothpaste being squeezed out. It's very, very viscous. It doesn't run very much. But now my last one, I tried real hard to make this right. Now, what this says underneath my face here is high silica, high water content. Now, when you have that, the water content gives you a lot of pressure, but the silica holds it back. And so when it releases, it tends to release explosively. So the biggest eruptions, the famous eruptions that disrupt life and alter ecosystems, these are often the result of these high silica, high water content ones. Like, for instance, Krakatoa. We'll see a picture of the newer version of it, but the original version of it, the eruption was so violent, it was literally heard around the world. There was reports of people who had no idea the eruption happened. It happened in the 1800s before telegraph. Be like, man, I just heard a weird boom, and they wrote it down in this journals. Okay, so that's how powerful these things can be. So if we look at a hot spot or Rift Valley eruptions or mid-ocean ridge, say like in Iceland, we tend to find that they're not very violent and they flow very easy. They have low silica, they have low water, so they're these beautiful, just running rivers of lava. Okay, what have I got here? Okay, so here's our running river of lava. Okay, let me see if it is. Okay, good. I don't have sound. So just look at that beautiful. Look at this drone footage. This beautiful, beautiful running rivers of lava. I have no idea what that says. I hope it wasn't anything inappropriate. Okay, so this is basically in Iceland. Okay, so it's essentially mantle material, low water content, low silica content, and it just flows in rivers. Okay, now I'm trying to get through it. Now let's talk about subduction zone volcanoes. They're quite different. Okay, so here's Mount St. Helens in the state where my house is in Washington State. Unfortunately, this happened before people had the ability to do video recordings that were to digital, so they just someone had to take a few pictures, they stitched them together. But here's Mount Pinatubo. Now these things are powerful. There's a lot of silica, so that it holds back. It's very viscous. There's a lot of water in there because subduction zones carry water down with them, right? So when you're carrying ocean floor material, there's a lot of water in there, so there's a lot of pressure. There's also a lot of carbon dioxide for reasons we'll talk about later. Basically, when limestone dissolves or melts, rather, it makes carbon dioxide. So there's a lot of pressure. So you get these big, powerful, explosive volcanoes are always associated with subduction zones. Well, I shouldn't say always, usually. So I don't think this one will work. I tried this before; it didn't work. I'll try, but it'll probably say we can't watch it. Yeah, that's what I thought. Okay. But let's go to this one here. So this is Anak Krakatoa. This is the baby Krakatoa, and I just want you to see this one here. You should just go and look at this on the presentation. But it's pretty dramatic here. Okay, I like here they actually caught it the moment it happened. That almost never happens. But someone's just watching, and to be honest, this isn't really even nearly as violent as it can be. But here you go. Now, I just want to point out those things you see coming down are boulders. Some of them are the size of buildings. These are huge, red hot building size bombs basically flying down the hillside, and the stuff you see coming down the hillside, you can see some red hot rock in there. There are chunks of lava in there, but the stuff you see coming down is what we call pyroclastic flow. It's basically hot gases with what's known as ash mixed in with it. So it's not really lava. The lava tends to get blown into the air. Okay, you should definitely go back and look at that some more because it's quite dramatic. Okay, so now let's talk about this stuff here. This stuff that gets blown out of these volcanoes is called volcanic ash. It's something that's very characteristic of high silica eruptions. Basically, what happens is when the lava is blown upwards, it just freezes in little tiny droplets in the air. It freezes so quickly, it doesn't have a chance to form actual mineral crystals. So we call it volcanic glass, and the stuff just drifts sometimes across the whole world. So ash is just basically quick flash frozen droplets of liquid lava. And so let's just talk about some of the alterations to the environment that volcanoes can produce. Okay, let's just start with the very powerful eruptions like, say, Mount Pinatubo or Krakatoa. They are known to cause changes. Both of those volcanoes I just mentioned changed global temperatures demonstrably in their aftermath. And the reason is so much ash was pushed up into the stratosphere that it literally enveloped the planet and reflected sunlight back into space. So less energy reached the Earth's surface, so less energy on the surface, the planet got colder. It happened in Mount Pinatubo in the 1990s. It happened with Krakatoa in the I want to say 70s. I'm not really sure exactly when the first major Krakatoa explosion was, but that's one thing they can do. They can drop the global temperature. They can also raise it, actually. So there's been times in the past where they think that volcanic eruptions can either trigger ice ages by putting a lot of ash into the stratosphere, or they could also trigger global warming by putting a lot of carbon dioxide in the atmosphere. So both are possible for volcanic eruptions. Now, that ash, when it comes down, it's going to block productivity. If sunlight can't reach these plants, they're going to stop photosynthesis and die. So this poor man just lost his pineapple crop. And it may be he can grow more next year, but maybe that the ash is so deep he just can't even do it. Ash is not the same thing as soil, so it could be years before this man is able to grow a crop again. So it can break houses down and stuff like that, but it can also, and it can hurt people's lungs when they breathe it in, but also too it's damaging to natural ecosystems because it prevents productivity. Another thing that happens is it causes forest fires, which release carbon dioxide in the atmosphere and can change the climate that way. But also, too, when this lava here freezes, as it will soon after this picture is taken, you basically just have this mass of rock that may be 40 feet thick that nothing can grow on or through, and so you basically have this area of land that cannot support any productivity. Things can't grow on it because there's no soil. We'll talk about that later. But it can be uh, uh, basically ungrowable for decades, centuries, or even thousands of years, depending on the environment in which it happens. Now, another thing that can happen is tsunamis. Here's a tragic tsunami that happened on Boxing Day, the day after Christmas in 2004, um, in the Indian Ocean. It was one of the most dramatic tsunamis, certainly in my lifetime. That one, the one that happened in Japan. And basically, anytime you disturb the seafloor, and volcanic eruptions certainly can do that, you end up getting tsunamis. Like the Krakatoa, the one that's heard around the world, it kills thousands and thousands of people with the tsunamis that it produced. And so let's just talk about what tsunamis do to the natural environment. Well, they definitely disrupt coastal environments. They rip up mangroves. They reshape coastlines, and they also disrupt tropical reef. And tropical reef is very slow to recover. So, for instance, I was just in Sri Lanka a couple years ago, and that was like 17 years, 16 years after the Boxing Day tsunami, and the reef was still not recovered at all. Okay, it basically, that tsunami came through, it just upended everything, and coral was really slow to grow. So that, like, all these ecosystems in the area were put under stress as a result of that. Well, now let's talk something good about volcanoes. Apart from the fact they're awesome to see, you want to see them. The other thing is that they can be very beneficial in this sense. I remember as a kid thinking, like, if volcanoes are so dangerous, why are those idiots making their farms on the side of them? I was such an arrogant jerk. Okay, here's the reason. You know why? Because one of the two limiting factors in plant growth usually are nitrogen and phosphorus. Now, nitrogen is captured, remember, by nitrogen-fixing bacteria. All right, so anywhere in the world, you're going to get these bacteria. You're going to get your nitrogen back. Okay, not true for phosphorus. Phosphorus comes from rock material dissolving, and it turns out ash, with its high surface area to volume ratio, when rain lands on it, it leaches that phosphorus out quite easily. So the reason people like to farm, like in Indonesia, the reason people like to farm where you have volcanoes is you have high fertility, but you have natural fertilizers. You cannot make DNA without phosphorus, and there's lots of phosphorus coming into the soil after volcanic eruptions. Thanks for watching. I hope this one worked. I did this whole thing last time and it didn't work. It better work this time. Okay, let's see.